Hi, and welcome to 2.4 Acceleration. In this lesson, students will be able to calculate the acceleration of an object. So normally in the classroom, I have a constant velocity cart that moves at a constant velocity, and then I'll break out my fan cart, which doesn't move at a constant velocity. So instead of doing that in the classroom, I decided to make a nice PowerPoint slide. What else is new? So it says, how would you describe the motion of the green car? Think about it. How would you describe that motion? Maybe you'd say it's moving to the right. You would be correct. Tell me about the magnitude of the velocity. So yeah, you're telling me the direction of the velocity is to the right. The magnitude, is the magnitude changing? In other words, is it speeding up or slowing down at all? It seems to be moving at a pretty constant velocity. So that's how I would describe the motion. It's moving at a constant velocity to the right. Now for this blue car, do you notice a difference? It's still moving to the right, so the direction is the same, but what's happening to the magnitude of the velocity? You might say it's speeding up to the right, and you'd be correct. You might even say it's accelerating to the right, which is also correct. So there's two different motions happening here. The green car is a constant velocity, and the blue car is accelerating. So it's changing its velocity. Well, how fast are you changing your velocity, right? Are you gradually increasing your speed over a long period of time? Or is it like a roller coaster where all of a sudden, boom, your speed changes really fast? So we need a way to quantify how fast you're changing your velocity. And that's the acceleration, your rate of change of velocity. So you could write this down in your notebook. Acceleration, we use the letter A to represent acceleration. It's the rate at which velocity changes over time. An object accelerates if its speed, direction, or both changes. An acceleration is a vector quantity, which means it has a magnitude and a direction. So the formula, A is equal to delta V over T, is the change in velocity divided by the time for that required change. You might see it as Vf minus Vi, the final velocity minus the initial velocity, because that's just writing out the change. The change is the final minus the initial. And in physics, it's always going to be final minus initial in that order, and that's super important because that will help with the direction, because you could either get a positive number or a negative number, depending on if you flip these two variables, and the positive or negative denotes the direction. So it does matter which one comes first. You want to always do final minus initial. The units are meters per second squared, and it's located on the back of your reference table right here. Now again, acceleration's here, delta V, the velocity or speed down there, and then time. Don't forget this is in alphabetical order. Okay, so you could look up anything you're looking for pretty easily if you remember that. So let's talk about the units. I brushed right over that. Meters per second squared, what the heck is that? So it measures the change in velocity in a certain amount of time. So let's look at an example. A bike is speeding up, and it speeds up by 2 meters per second every second. So if you were going to make a data table like that, maybe it starts at rest, and then after 1 second, it travels at 2 meters per second. After 2 seconds, it's speeding up. Now it's 4 meters per second, and so on. So you could say it speeds up 2 meters per second every second, or 2 meters per second per second. And you could write your units like that, and that would be totally fine. But anybody who's taken a physics class before might look at you a little funny because that's not really how we do it. We write meters per second squared. And then if you want to see where the squared comes from, okay, we're just cross multiply. We're trying to get rid of this improper fraction. So you multiply by seconds. That cancels out. And whatever you do to the top, you have to do to the bottom to make it equal. So that's why it's a second times a second. And that's where meters per second squared comes from. But don't forget, it's really meters per second per second. How much did you change your velocity in 1 second? That's what acceleration is telling you, your change in velocity, your rate of change of velocity. So just a review of the scalars and vectors we've done so far. Distance is a scalar. Displacement is the vector version of distance. Speed is a scalar. Velocity is the vector version of speed. And acceleration is a vector, and there's no real scalar equivalent. But for acceleration, direction does matter. You could see 5 meters per second squared west is the same as saying negative 5 meters per second squared. Okay, so with the vectors, if we have a north, south, east, west, that's going to correlate to the XY graph that we're used to. And by convention, anything that's moving north or east, we say is moving in the positive direction. And anything that's moving west or south, we say is moving in the negative direction. Or even left or right, up, down. Anything moving up or to the right is seen as positive mathematically, and anything left or down we make negative. And that's the convention that we use, so that in our equations that we're going to use, if it pops out a negative number, you're going in the negative direction, whether the problem says west or left or even just in the negative x direction. All right, so the direction matters, the signs matter, plus or minus. All right, so we have this little table here. Is it speeding up or slowing down? You're accelerating, you're decelerating. Really, decelerating is the same as accelerating, but you're accelerating opposite your velocity. So what would this look like if your velocity is to the right and you're accelerating to the right? That means you're speeding up. So it looks like this. Now, just because you have a positive acceleration doesn't mean that you're speeding up. What if you were moving to the left? So your velocity is to the left, but you're also accelerating to the left in the same direction as your velocity. Your velocity is becoming more and more negative, which means that the magnitude of your velocity is increasing in the negative direction. So that means you're speeding up in the negative direction. And that's totally fine. You could say you're speeding up in the western direction. Maybe that makes it more sense, because when we think negative, we think it's going down, right? But in physics, when you think negative, you should be thinking about the direction. So yeah, you're speeding up in the westward direction or in the left direction. Your velocity is increasing. Now, how do you slow down? Your velocity and your acceleration have to be moving against each other. So you want your velocity is to the right, but your acceleration is slowing you down. It's pointing to the left. It looks like that. You could have the opposite. So if you're moving to the left initially, but you're accelerating to the right, since they're opposing vectors, you're going to slow down. Okay, so yeah, your velocity is pointing to the left there. Now, if you are not accelerating, if your acceleration is 0, whether you're moving to the left or to the right, if your acceleration is 0, that means you're not changing your velocity. So you're just constantly moving. There's our constant velocity car again from the beginning. And that's to the right, but your velocity could also be to the left. And as long as your acceleration is 0, you could describe the motion as constant velocity. And then if it's your velocity, now this has been your initial velocity. If your initial velocity is 0, that means you're starting from rest and you're speeding up. And if your acceleration is in the negative or positive direction, that'll tell you which direction you're going to go. So looks like that. Or in the negative acceleration direction, could look like that. Speeding up from rest. So that's a term that we'll use. At rest means your velocity is 0. And then if your initial velocity is 0 and your acceleration is 0, you're just going to remain at rest. You're not changing your velocity at all, and your velocity was 0, so you're just remaining at rest. So the thing to remember here is you speed up if your acceleration and velocity are in the same direction. So here they're in the same direction, here they're in the same direction, they're going to speed up. And you're slowing down if your acceleration and your velocity are in opposite directions. Let's do an example. It says a car traveling east. So as soon as you see east, you should now be thinking, okay, it's positive. the velocity is positive. It's traveling east in a straight line on a highway, and it increases its speed from 23 meters per second to 30 meters per second in 2 seconds. So we're going to do the guess method here. I see two velocities, don't you? Meters per second, meters per second. That's another key that you could look for when you're writing your given information down, is look at the units. So 23 meters per second, what does that equal to? Well, for now, we'll just write velocity, but we have another one over here. So how do we describe the difference between these two velocities? If you remember from the notes slide, when I introduced acceleration, we wrote down delta V is equal to VF minus VI, the final minus the initial. So which one is the initial velocity? It says it's increasing its speed from 23 meters per second to 30 meters per second. So this is VI, and then the final velocity is 30. So we would make our subscripts like that. The subscripts are very important. Now they also tell us a time, 2 seconds, so we could write t is equal to 2 seconds. And what is the unknown information? It says, what is the car's average acceleration? So we're looking for A. So we have our givens, we have our unknown. Now we need to find the equation. So the equation we're going to use is A is equal to delta V over T, which expands out into VF minus VI, always in that order, VF minus VI over T. So that's the equation. Then we substitute in A is equal to VF is 30, so you have to put that first, minus 23 over 2. So you get 7 divided by 2. So your acceleration, when you solve, is 3.5. And what are the units? Ask yourself, what are the units? Meters per second squared. And then it's in the positive direction. So two things regarding the units. Since we wrote the units for the given information on the side here, we'll get full points. If you didn't write these units, you're not going to get full points on the test or quiz. That's how the Regents exam grades it, so that's how I grade it. The second thing is its acceleration. This little 2 will cost you a point if you don't write it. You cannot write 3.5 meters per second and call it a day there. This, to me, looks like a velocity quantity because the units are meters per second. Okay? You need to write the square to get points for units because these units are not showing me their acceleration. They're trying to show me a velocity, which is not what we want. So you got to write the square and you got to write the units for the given information in addition to, obviously, the units for the final answer. Example 2, a car traveling with a velocity of 20 meters per second east in a straight line on a highway accelerates at a rate of 2 meters per second squared west for 3 seconds. If it helps, you could underline the directions so that you don't forget them, because this could be a little bit tricky. They're telling you an initial velocity, 20 meters per second east. So VI is equal to 20 meters per second. It's east, so we'll make it positive. Then it's telling you the acceleration is 2 meters per second squared. And it's tricky because they could make it easy and call it negative 2 meters per second squared, but they call it 2 meters per second squared west. And it's up to you to remember, oh, west is in the negative direction. As we talked about before, the west is pointing to the left, which is in the negative x-axis. If it was south, it would also be negative. So you have to remember to plug your negative sign in when you're doing the math. They also tell you that it's doing this motion for 3 seconds. So the first question asks, is the car slowing down or speeding up? And all you have to do is look at the signs of the velocity and the acceleration. Those signs are pointing in opposite directions, so we know right away that it should be slowing down, as we discussed on the previous slide, or a couple slides ago. Number 2, what is the final velocity of the car after 3 seconds? So now they're finally asking for some unknown information, the final velocity. Okay, and then we're going to find the equation that we want to use. So A is equal to delta V over T. A is equal to VF minus VI over T. Then we'll substitute in at this point. Negative 2 is equal to VF, which is what we're looking for, minus 20 over 3. Minus positive 20, right? So don't forget, just because this is positive, don't make this a positive. And you could, in this step, solve for VF first and then plug in the numbers, which is totally fine way to do it too. But now we can cross multiply and we get negative 6 is equal to VF minus 20. So you add 20 to both sides, and you get VF is equal to 14 meters per second. Okay, so did our prediction come true? We said it was slowing down. Well, your initial velocity was 20 meters per second. Now we're moving at only 14 meters per second. So yes, the car did end up slowing down, and we are really good at physics. And that's about it. Thanks for watching, and have a great day.